So before we start, let us have a recap of previous experiments about the transistor. When we use as an AC amplifier, the transistors, biasing resistors RC, RE, R1, R2 are designed or calculated in such a way that the voltages BC, BB, BE will set the transistor in active mode. So in active mode only, we can use the transistor as an amplifier. And what are the conditions to achieve active mode? So BC must be greater than BB. We have BBE 0.7. BCE must be at least 1/2 of BCC or close to 1/2. As you can see this location. And the collector base, reverse bias, and base emitter, the base emitter junction will be forward bias. If that is the case, we satisfy the condition to work as an active mode, and we can have a small signal being amplified. We have an inverted amplification using the BJT amplifier. Okay? Now, the transistor can operate as a switching devices with proper acting signals, usually in the form of pulses. When used as a switch, the transistor operates in either on region or off region. So, in which condition we have an on region? Look at this waveform. Look at this graph. So, it is in on region when we are in saturation, right? On region, that means we are in saturation. But off region, that means we are in the cutoff region. So, a cutoff region, that means the transistor is fully off. So, the areas of operation of transistor, which are known as saturation region and cutoff region, and this means that we can ignore the operating Q point biasing for all the voltage divider circuitry required for amplification. So we don't need to use the transistor to amplify a signal. We only need it to use as a switch. So we just take care about the saturation region and the cutoff region. And so since it's being used as a switch, let's say this is the load, we have to control the collector current. And the collector current is being controlled by the base current. So we will have an input voltage, right, in series with the base resistor in order to supply a current, a base current that can control the collector current. If the amount of current is not enough, IB is very, very less, it doesn't reach a certain saturation point, the transistor is said to be open, just like a switch, an open switch. However, if the IB has reached its saturation condition, that the transistor is working as a closed circuit. So it is a closed switch, right? As you can see here, different values of IB. As we increase the value of IB, right? In this case, the IB is 0. IB is not enough to trigger the collector current. So we have here, this is in off condition. So as we increase IB from IB1 to IB3 to IB4, IB6, let's say we reach the IB6. So this is already the maximum current. This is the saturation condition, fully saturation condition. This is the maximum current. So if your requirement here, what is the importance of achieving the maximum current? Suppose the load RC requires a current of, let's say, 100 milliampere, right? At 100 milliampere. So this is the maximum current that should flow. So this should, in this condition, the transistor should be in saturation mode so that it can provide the required 100 milliampere. Now, solid-state semiconductor switches are one of the main applications for the use of transistor as a switch. DC output on or off. Some output devices such as LEDs only require few milliamps as logic level DC voltage and can therefore be driven directly by the output of a logic gate, right? So in the off state, again, resistance is very high. Typically in what? In a level of 10 mega ohm. The base current controls the condition of the transistor. When IB equal to 0, the transistor will be off, and BCE. So the voltage between BCE will be equal to BCC. In the on stage, the resistance between the collector and emitter is very low, in a value of 1 ohm to 50 ohm. So the value of IB must be greater than IB saturation, and the transistor will be in on stage. In this case, BCE is equal to B saturation, which is very, very close to 0. Okay? Now, in order for the base current to flow, the base input terminal must be made more positive than the emitter. So this portion here must be more positive compared to emitter. So what are we going to do? We have to put an input voltage here, and by increasing it above 0.7 volts needed for the silicon device, suppose this is silicon transistor, by varying this base emitter voltage, the base current is also altered, in which in turn controls the amount of collector current flowing through the transistor, right? As I discussed previously, the base resistor determines how much input voltage is required, and the corresponding base current to switch the transistor fully on when the maximum collector current flows to the transistor. So, let us have an example of using a transistor as a switch. Assuming we have the beta of the transistor 200, the required IC is 4 milliampere, and IB is 20 microampere, right? The saturation current IB is 20 microampere. So what will be the value of your base current? You need to design your circuit and to provide the exact value of RB so that you will have IB equal to 20. So we will have how to calculate RB. RB will be equal to B in, this is B in here, B in, minus BBE, right? Over IB, you will have, let's say here, the input voltage is 2.5, right, in this example. So 2.5 minus 0.7 over 20 microampere will give me a 90 kilo ohm resistor. So I need to put here a 90 kilo ohm resistor so that I can achieve a base current of 20 microampere, which is enough to saturate the transistor so that an IC of equal to 4 milliampere will flow on the load, on the switch, right? So we will have IC saturation at 4 milliampere. Okay? Now, assuming again we have a beta of 200, find the minimum base current. In this case, we will calculate the base current required to turn on the transistor for an IC of 200 milliampere. Suppose this is the load requirement. The load requirement is 200 milliampere of current. When input voltage is 5, so we increase the voltage to 5 here, V in equal to 5, and here we require a 200 milliampere. So first of all, what will be the value of RB and what will be the value of IB? Now to calculate IB, we have to use the relationship IC over beta. So 200 milli over 200, we will have 1 milliampere. So that will be our base current. So upon knowing base current, RB will be B in minus BBE over IB. We will have 5 minus 0.7, 4.3 kilo ohm. So I need to put here 4.3 kilo ohm in order to have a current which is 1 milliampere, which is enough to saturate the transistor, and IC can flow easily all throughout to the emitter, right? Transistor switches are used for a wide variety of applications, such as interfacing with large current or high voltage devices like motors, relays, lamp, to low voltage application like a digital IC. In this case, in our experiment, we will be working in a digital IC, right? So, but let us have a summary, okay? For the cutoff characteristic, the input and the base are grounded, meaning 0. Right? For the cutoff characteristic, the B input 0 or must be less than 0.7. Less than 0.7. So if that is the case, it will be open, right? Base emitter voltage less than 0.7. If the base emitter voltage is less than 0.7, the condition is cut off. Base collector junction reverse bias. So base collector junction here, reverse bias, so it's on cut off, and transistor is fully off or cut off region, no collector current, IC equal to 0, and the B output is equal to BC, which is equal to BCC, let's say 1. What does it mean 1? 1 means there is output from this terminal. So when this is open, right, B output, so the switch is open, we can obtain a voltage here, right? We will have a B out here. Okay, let's say we call this the B output equal to 1 when this is open. If this becomes short, there will be no output here. So B output will become 0. That is in the other case when saturation, in the saturation condition. So in saturation condition, the base input are connected to BCC, or if you have another source here, in this case, in this connection, it's connected to BCC, or if you have an input here, just like what I did in the previous example, I have a separate source here, which is enough to overcome also a BBE equal to 0.7, and a base emitter junction is forward bias, base emitter junction forward bias, and base collector junction is also forward bias. For base collector also forward bias, transistor is on. The maximum collector current will be what? Equal to IC is equal to BCC over RC, maximum collector current. The BCE is equal to 0 because it is shorted here. It is shorted here, BCE. This is BCE. B out is BCE. BCE equal to 0. Right? So it will be equal to 0. So 0 and 1. Right? When the switch is open, the output is 1. When the switch is shorted, the output is 0. Transistor operates as a closed switch. So these are the things. Now, let me do a PSPice to further elaborate this scenario.